Is my screen visible? Okay. So let's start with decision trees. We can use decision trees for solving the regression as well as classification problems. I hope everyone is familiar with conditional statements, if else and nested if else. So we are going to do this in the form of decision trees. Here we need to answer the question whether the person is fit or not. So first of all, we have a specific root node and the condition is age less than 30. After that, we will have one condition for yes and one for no. If this is yes, we'll go to this side, and if no, then the other side. That's how we'll reach to the leaf node. Here you can see that this entire code got converted to this kind of tree. So we are just solving a specific problem using nested if else and in the visualized form using decision trees. Okay. Suppose we have this data set. So how do we solve this? I'm sorry. Suppose we have this data set. So how do we solve this? This one is a classification problem. So this is our output feature, whether the person will go out for running or not. So first let's consider any specific feature, let's say weather. Now how many are having no's and how many are having yes? In this we have 3 yes and 4 no's. So based now in this feature we have 3 categories, sunny, cloudy and rainy. So based on these 3 categories I'll create 3 nodes and do the splitting. Now we'll count the number of yes and no's for each node. So here sunny has 1 yes and 2 no's, cloudy has 2 yes and 0 no's, and rainy has 0 yes and 2 no's. So now we have pure nodes and impure nodes. So the node which has either all yes and 0 no's or all no's and 0 yes is a pure node. In this case, cloudy and rainy are pure nodes and sunny is an impure node. Remember, pure node can't be splitted further. Now we need to split sunny feature further. So I'm going to take feature temperature on the basis of which I'll do further splitting. And we'll keep on splitting until we finally get a pure leaf node as we got in the cases of cloudy and rainy. Okay. Now we have two questions. How do we calculate the purity or how do we know that this is a pure split? And the other question is how the features are selected. So to know about the purity, we have two methods, entropy and Gini impurity. For selecting features, we use something called as information gain. Now let's understand entropy and Gini impurity. Here we have the formula for entropy, minus P positive log base 2 P positive minus P negative log base 2 P negative. Now in this formula, P positive and P negative represents the probability of yes and no respectively. Let's understand this with an example. Suppose we have a feature F1 which is further splitted in categories C1 and C2. The number of yes and no's are already given. So let's check whether C2 is pure or not. So here P positive is probability of yes. How do we calculate probability? Total number of yes divided by total number of samples, which is 3 by 3, 3 by 3 in the case of C2. And similarly, we'll find P negative, which is 0 by 3. After putting these values in the formula, we get entropy is equals to 0. So we can say that for pure split, entropy is 0. Now let's calculate for C1. From here you can see that the value of P positive is going to be 3 by 6 and P negative is also going to be 3 by 6. So on solving, we get entropy is equals to 1. Here we can say that for a completely impure split, where probability of yes and no are 50% each, entropy is equals to 1. So this is the graph for entropy versus P positive. Here also you can see that for P positive is equals to 1 by 2, entropy is 1. Now let's understand Gini impurity. This is the formula for Gini impurity. And if the value of n is equals to 2, that is if outputs are only yes and no, then we can use the second formula. For this given node, we have this node in which we have 2 yes and 2 no's. P positive is 2 by 4 and P negative is 2 by 4. So on calculating, we get Gini impurity as 0.5. We saw earlier that for complete impure split, entropy is 1 and now Gini impurity is 0.5. This is the graph for Gini impurity. So now when do we use Gini impurity and when do we use entropy? as it is clear from the formula that we are using log functions in entropy. So calculating entropy will take comparatively more time than Guinea impurity. Therefore, it is suggested to use Guinea impurity if you have large number of features. Okay. Next thing is how the features are selected. Any doubts till now? Okay, so we'll continue. Next is how the features are selected. For selecting features, we use information gain. This is the formula for information gain. Here, h of s is the entropy of the root node. Mod of SV is the total number of samples in category I or category V, we can say. And S is the total number of samples in the root node. H of SV is the entropy of category I or V. So here we have calculated the entropy of root node, which is 0.94, and entropy of leaf nodes C1, C2, which is 0.81 and 1 respectively. So on calculating information gain for feature F1 and F2, so for F1 we are getting 0.049 and F2 we are getting 0.051. So we can see that information gain for F2 is greater than that of F1. So we'll use feature 2 to start the splitting. Okay, that's how we select our features to split. Now if we have feature with continuous data, then first step is to sort the data. So after sorting, suppose we have this feature, continuous feature, then after sorting, we will get the values as 1.3, 2.3, 3, 4, 5, and 7. Now we'll take these values one by one and apply the conditions of less than or greater than for splitting the data. Here first we'll take 1.3. So there will be only one output with less than equals to 1.3 as the data is sorted and rest are greater than 1.3. So after this we'll find the information gain for this. Then we'll take the next value which is 2.3 and get this particular decision tree and again calculate the information gain for this. So we'll keep on calculating the information gains for all these values and find the highest information gain. Next we have decision tree regressor, that is when the output is continuous. First step is to calculate the mean of these output values and calculate mean squared error or mean absolute error. So this F1 has mean, and here we don't have Guinea impurity or entropy. We have MSE or MAE, that is mean squared error or mean absolute error. So on splitting based on different categories, we will again calculate MSE for the records that lie in them. As the MSE or MAE reduces, we are reaching towards the leaf node. Finally, whatever the mean is present over here will be your output. Okay. Next, decision tree leads to overfitting. And to prevent overfitting, we use two methods, either post-pruning or pre-pruning. First, post-pruning. Suppose we have this type of scenario where we have 7 yes and 2 no's in a particular node. So there are high chances that the output for this node is yes. So we don't need to split it further and we can cut off this branch here only. This technique is called post-pruning. Now we have pre-pruning, which is done with the help of hyperparameters. What kind of hyperparameters? We can say number of decision trees we should use, maximum depth of the tree, or maximum leaf nodes. All this can be done with the help of grid search CV. Okay. Any doubts till now? So now we'll understand the practical implementation of decision trees. Okay. So first we are going to import all the necessary libraries, NumPy, Pandas, Matplotlib and Seaborn for visualization. And then train test split for splitting the dataset into training and test set. Grid search CV for hyperparameter tuning. Label encoder, one hot encoder for encoding categorical data. Column transfer for feature transformation. decision tree classifier for training our model, and accuracy score, confusion matrix, and classification report to find the accuracy in the report. So here we are going to use label encoder as well as one-hot encoder. So label encoding converts each categorical value into numerical value. Each category is assigned a unique integer. And in one-hot encoding, each category gets its own column and the presence of a category is marked with a 1 while all other categories are marked with 0. Okay, so then we'll do pre-processing. So first we'll upload our data set. Then we are going to remove all the useless features from our data set and find the summary and all. Next step is to handle the missing values. Handle missing values and coding the categorical data. And after that, we'll split the data into training and test sets. I want to tell you an important thing. Yesterday, when we did the practical implementation of KNN, I've told you that first we'll split our data, then handle our missing values. But it is not true in all cases. It may sometimes lead to data leakage, so it depends whether to split data before or after handling the missing values. In this implementation, data is split after handling the missing values. Well, in yesterday's KNN's implementation, we have split it before handling the missing values. Next, we have post pruning for preventing overfitting. So we'll create the decision tree classifier instance with the parameter ccp underscore alpha, which is the complexity parameter used for minimal cost complexity pruning. Then we'll train our model on the training set and predict the values for the test set. These are our predicted values. After that, we'll find the accuracy score, confusion matrix, and classification report. So we are getting an accuracy of 0.79, that is 79%. Okay. Other method to prevent overfitting is pre-pruning. So for pre-pruning, I told you we can do pre-pruning with the help of hyperparameters, that is grid search, CV, and all. So these are the parameters which we are going to test and find the best ones among them. So again, I'll create decision tree classifier instance, then grid search CV instance, and fit a training data and find the best parameters. So the parameters we are getting are maximum depth as 3, minimum sample sleeve as 2, minimum sample split as 2, and then we'll predict the test set data and find the accuracy score. So here also we are getting an accuracy of 79%. So you can see the accuracy in pre-pruning and post-pruning are almost same. So you can use any of these methods to prevent the overfitting. Okay. Any doubt in the practical implementation of this engine? Okay, so now we'll understand the intuition of random forest. Okay, random forest. But before that, we'll discuss about ensemble techniques. In ensemble techniques, multiple models are combined to increase the accuracy of a result. Ensemble techniques are of two types, bagging and boosting. Models are trained parallelly in bagging, whereas sequentially in boosting. So let's understand bagging. This is our training data. Now I'll take up few rows. Basically, I'll do row sampling and push it to model M1. Suppose I have a data set of 10,000 rows and I am doing row sampling of 1000 rows and giving it to M1. Again, I am going to do row sampling and give it to M2. Sorry. And remember, some of the rows may get repeated from this B1 to B2. Okay. Similarly, we'll do for other models also. Now the outputs of all the models will be aggregated and the final output will be the one with majority voting in case of classification. And in case of regression, we'll find the mean of these outputs. Let's say output of M1 is 0, M2 is 0, and M3 is 1. So our final output will be 0 as per the majority voting. If we have continuous values in the output, then output will be their mean. This step is called as bootstrap aggregating, as you are aggregating all the outputs coming from specific models. Now we have boosting. So boosting is a sequential combination of models. As you can see, our models are connected sequentially. So this M1, M2, M3, we basically mention them as weak learners in boosting. And once I combine all these weak learners, it becomes a strong learner. Okay. Then in bagging, we use algorithms like random forest classification, random forest regression, and in boosting, we use ADA boost, gradient boost, extreme gradient boost, or XD boost. Before going to random forest, first let's discuss what is the main problem with decision trees. As we have discussed earlier, decision tree leads to overfitting, right? Overfitting means what? For training data, the accuracy is high, and for test data, the accuracy is low. So we can basically say it as low bias and high variance. Obviously, we can do pruning and all for preventing overfitting, but again, it is an extensive task if you have a large number of features. We know that our generalized model should have low bias and low variance. So for converting this high variance to low variance, we use random forest classifier or regressor. Now what does random forest do? Random forest is a bagging technique. Let's say here we have a data set and multiple models M1, M2 and all. Now all these models are decision trees. In bagging we have many different models, but in random forest these models are decision trees. Decision tree leads to overfitting, but if we combine them in the form of bootstrap aggregator, this high variance will be converted to low variance. The other thing is, in random forest we do row sampling plus feature sampling. That is, we will select some set of rows as well as some set of features and give it to M1. Similarly, we'll do row sampling and feature sampling for other models too. In bagging, we used to do only row sampling, but in random forest, we'll use row sampling plus feature sampling. And again, remember your features may also get repeated, just like your rows can get repeated. Then again, a final output will be decided with majority voting or mean, same as we did in bagging. Now we'll see some pros and cons of this algorithm. First is high accuracy because they create multiple decision trees and average the results. Then it is robust to overfitting, can handle missing values, handle large data sets, and most importantly, robust to outliers. But as we have seen, it is more complex than a single decision tree, less interpretable, unsuitable for imbalanced as well as sparse data sets. So that's all for the intuition of random forest. Any doubts? Okay, now we'll see the practical implementation of random forest. Okay. So first step is to import all the necessary libraries, NumPy, Pandas, label encoder for encoding categorical data, train test split for splitting the data set, grid search CV, randomized search CV. So grid search CV is used for hyperparameter tuning, as I've already told you, and randomized search CV is also used for hyperparameter tuning. So I'll tell you later why we are using both of them, like the difference between both of them. Then we have random forest classifier for training our model, and accuracy underscore score to find the accuracy of our model. Then I was getting few warnings while running this code, so I have used these two lines: import warnings, warnings dot filter warnings, and in bracket ignore, to hide, or we can say ignore those warnings. Later on, you can check by commenting it out. So that how does it work? Then we'll upload our data set. After that, we'll do some data pre-processing. The same thing, handling missing values, encoding the data. Then after that, splitting our data so that we don't face the data leakage issue. Then next is model training. So first we'll initialize an object with default parameters. Okay, and then train our model on the training set and predict the values of the test set. So here we are getting an accuracy of 0.80, that is 80%. And then we'll again create an instance of the random forest classifier using some parameters like maximum sample 0.75, random state as 42, and again predict the values and find the accuracy score. Now we are getting an accuracy of 82%. So here you can see by adding parameters, we have increased the accuracy of our model. Okay, so now we'll do hyperparameter tuning. So these are the parameters which we are going to test in this and find the best ones. Again, I've created an instance of the random forest classifier, then grid search CV, train the model, and find the best parameters. So best parameters here are maximum depth as 8, maximum features as 1, maximum samples as zero point 0.5, and n estimators is 100. So we are getting a best score of 0.83, which is 83%. So here you can notice that after applying hyperparameter tuning, we are getting the best score as 83% with for the maximum samples of zero point 0.5. And when we have taken the maximum samples of 0.75 above, we were getting the accuracy of 82%, which is less than this. So that's how grid search CV helps us to find the optimal parameters for a model. Okay. Now the issue is if we have big data sets, then grid search CV becomes quite slow. So we can use random search CV instead of grid search CV. So I'll share this file with you so you can check it out later. It will take time now if I'll do this now. So now random search CV. These are the parameters we are going to test and find the best one. So then again we'll create an instance of random search CV, train the model and find the best parameters. And now we are getting the best score as 82%. So here the accuracy is less than grid search CV, but what matters is time. So it will take less time as compared to grid search CV. So you can use either grid search CV or random search CV as you want. So now any doubts in the practical implementation of random forest? You can ask your doubts if you have any. Okay. That's all from my side. Now Gauri will take the session further. Thank you. Gauri, you can continue.
Thank you. So for now, I'll be firstly I'm a good person. Is my voice audible? Okay. So for this session, I'll be taking evaluation metrics for both regression and classification. You have seen the scores like 82%, 80%, and all right. What are these values and what are they actually mean? Let's just look at what they actually mean. So firstly, we'll look at the evaluation methods for the regression problems. So firstly, we have multiple methods of just finding the evaluation limits like mean squared error, mean squared error, absolute error, R square, adjusted R square, and few cross validations and all. So we'll look into it one by one. Firstly, mean square error. This is just the measuring the accuracy of our model, which is trained. Firstly, we just train the model, right? At the end, we need to check how accurate our model is with respect to the real world scenario. So, these are all few methods of finding the accuracy. And for mean squared error, we'll just give just you can look into this formula as well. We'll just square upon the each and every error we'll get. Let's say y is our actual are getting output, and y cap is the actual real world scenario output. So to find the mean square error, we'll be taking 1 upon n. N represents the total number of cases we'll be looking at. So it's 1 upon n, and the summation of the y minus y cap whole square. It's just the squared error. So that is this is the mostly used one. Mean square error is the primarily used for regression problems. And yeah, I have told you the calculating formula. You can just look into this Google and get this. And next one. So yeah, that's what I told you. Root means good error. How do you calculate that part? It's taken. Let's look into this. It is calculated by taking the square root of the average of the differential. Basically, it's just y minus y cap whole square, and taking the summation of that and division of that by cap n value. So interpretation. It basically ranges from 0 to infinity because if it matches with the real world scenario examples, if it is 100% accurate, it will be leading us to 0. Else, it might lead to infinity as well if each and every case is incorrect. And this is the widely used in the regression analysis in our data science field, and it's used for predictions, comparisons, and all. Next, the next one is the mean absolute error. It's just 1 upon n sigma of y minus y cap. And that y minus y cap is taken as an absolute value. I guess we will have an example. Okay. So this is calculated as the absolute error of predicted and the actual values, which is y and y cap. So we'll be taking that difference as an absolute value. Means we'll be taking the magnitude, not the positive or negative one. And next, which is the scale dependent. That means it will be depending on the units which we take the target variable units. And later, unlike like mean square and mean absolute, like mean square and square mean error, this mean absolute is little less influenced because they are the much proficient ways we will be looking at because they are much more accurate than the mean absolute error. And in the real world scenarios, this matters more than square, but we'll be mostly looking at the square errors. Next, R square. R square is also known to be the quotient of determination. Because it is a statistical measure, we will be taking the composition of the variance as dependent variables. Let's say, so it also ranges from 0 to 1. And 0 indicates that model has none of its variability. That means each and every value is taken to be a perfectly calculated value. And 1 indicating that variability of the outcome variable. That means it's just the that means we'll be getting output slightly different from the actual real world scenario. And Asker it is a useful method for evaluating goodness fit of a regression model. So finding the goodness of fit, we'll be using this. And later adjusted R square. It's almost the same from the R square, but it's slightly different. You can see it's accounts for the number of predictors in the model. It also ranges from 0 to 1 over here mentioned. And then this is the basic point I think. It will be helpful in identifying the sort of models. And then coefficient of determination. This is also another way definition. One second. So this is denoted as an R square, and it will be much more useful in finding basic limits of fit for the regression models. And yeah, we'll look at the limitations of R square because that's the reason we'll be using the adjusted R square, right? It doesn't indicate whether the regression model is adequate. That's the reason we'll be considering the adjusted R square. So clear with that. Then cross validation. So cross validation it basically means we'll be splitting the actual data to parts. Let's say we have an example like n test data, and we'll just pick out random n value. Like for let's say we'll be picking out the third sample. We'll be training our model for the entire n values, excluding the third value. And we'll just test the model with the third value. Then we'll be getting an actual value. That manner, we'll be taking out each and every value from the actual n values, and then we'll keep on just cross validating for each and every value. That's the cross validation part, and that's all iterative. Like we'll just iterate from the first value to the nth value. We'll keep on repeating this process multiple times. And each and every splitting will be calculating the mean square error, root mean square error, R square, and these all will be calculated. Next, next choosing the right methods. What's the actual right methods to be chosen? It's completely dependent on the type of problem we are dealing with. We'll be calculating each and every regression task, and then we'll look at which methods is completely best aligned to our model. And for understanding the methods, you need to be strengthened, like properly understanding each and every terminology of the metrics to look into this. And it's a balanced layer of you need to look at also. Next. Yeah, it's primarily important to choose the right metrics for your specific model because that's what uh, company people will be asking about. Like, what's your best accuracy of your model? That's the kind of questions they might ask you for your projects, which you will be getting them in their resume. Let's say you have a project A, and they might ask you what's about the project number, and at the end they can ask you what's the accuracy and what's your metrics of evaluation amount. Then you should be in a position of applying for these outliers at each and every part. Yeah, that's it for a regression. One second. So now let's look at the classification evaluation methods. So here we have a few methods as well, like accuracy, precision, recall, and effective. I guess you all have seen them in the model training part, which Olivia has shown. Now we'll be looking at each and every uh, keyword, what that actually means. Firstly, we'll be taking the confusion matrix as a basic example. Like we have a few n set of values which we need to train our model. So the accuracy means that how many values our actual model is getting our true values, not how many values it's getting our false. Let's say we have our 50 examples in which uh, let's say 30 are true and 20 are false. And we train the model in such a way that out of 30, only 25 is taken by the model as a true value, actual true values. And out of those actual 30, it has given me 5 as incorrect values. So in this confusion matrix, The positive and negative are given true and false, so row values. The actual TP contains 25 according to my model, which is trained, and the false negative. False negative goes for the best file, which I have taken as the actual positive, but my model gave me as negative. So that goes under this file. And I have told you that 20 are the actual negative, right? But it has given me out of those 20, 5 as a positive, but the rest 15 are actually corrected by my model as a negative values. So true negative carries the 15 and false positive, which are actually not the positive, but my model gave me as a positive value. So that 5 goes under that. So this is the way confusion matrix will be designed over. Uh, these are the four. It's a divided matrix. It's firstly accuracy. This is the widely used in our evaluation method components for the classification models. It's taken as the entire, like how much accuracy. It means the formula just goes as you can see in the middle part is the total number of correct predictions out of the total number of predictions made. If you look at the formula, it's TP upon the entire, like TP plus FP plus FN plus TN. And next, this is it's basically a good notebook, like each and every model is mainly asked for the accuracy. And next, precision. It's just means that how much accurately the positive values are being calculated over here. Let's look at the formula. It will be taken as the total number of uh, correctly positive taken under the total number of positive values. This is mainly done to about the false positive errors. Yeah, you can see the formula in the first box. Two positive values out of all the positive predictions. It just means TP upon TP plus FP. Okay, sorry. TP upon TP plus FP. And in the next case, it's basically taken to avoid the positive, false positive errors. It's especially important in the domains in which false positives have serious consequences, such as medical diagnosis or fraud detection. Let's say we have used this model in the fraud detection. Though the fraud is actually not done, but it has given the fraud has really done, that could really matter a lot in the actual data analytics field. So we need to be looking at each and every part and which accurately good, satisfies our model. That's the primary we need to look at. Next we go. This is also known to be sensitivity and it just measures the actual positive cases out of all the positive and the negative cases. So recall it's just TP upon TP plus Fn and interpretation. This indicates the model is good at not missing the positive values. We have taken all the positive values, and out of which the non-positive values are not actually considered that matters in the record, and it is primarily used in the cost of missing a positive value is high. See, whenever a cost of missing positive is really high, in that we need to look at the record value, what actual record value is. The next F principle. This is a harmonic mean of like just mean of precision and recall as a harmonic mean. It considers both the false positive and false negatives. It ranges from 0 to 1, and 1 indicating the best fit and 0 indicating the worst fit, respectively. Next, ROC curve. It is a graphical representation of a binary classification model. Let's say we need to classify a model into only two different parts, whether it is yes or no. In that cases, we'll be using this sort of model, and it plots just the two positive rates and the false positive rates. If it is a false positive, it is represented in the graph of the actuals model. And perfect classifier. For perfect classifier, the two positive values will be 1 and the false positive cases will be 0. And it is an obviously. Next, if it is closer to this perfect classifier, which is represented in the dot, that is a better model area. And next, area under the dot. So this is will be representing the classification model in the binary values, and will be taking a curve. So this uh, point 8 represents the ranking of like how much area is covered under the model is not considered over here. And it is basically useful because our threshold will where threshold value is independent. You can just look into this matter. And next, sensitivity and specificity. Just look at these values and balanced accuracy. So understanding balanced accuracy. So this is much priority used metric for evaluating the classification models. We'll be dealing with few imbalanced data as well in some of the times. Let's say out of 100 values, 90 or 95% of the cases goes to yes, and very few values are given under no conditions. Then we will be trying to just balance our data, because if that is the model given to train the model, even if it is a no condition based on the yes count, it obviously leads to yes in the majority cases. So to avoid those such kind of cases, we'll be understanding this balanced accuracy. This is furthermore topic. And next, confusion matrix. This is the holistic view of the model. With this just confusion matrix, we can completely know what our actual model accuracy is about. It's ROC curve. It is also the best way of doing this model training somewhere. And I wanted to show you one of my projects in which one second, in which I have taken the. So this is one of my projects named the celebrity classification. This just means that I'll be training my model with a few uh, celebrities, like sports celebrities, and my final project should just take a picture of a celebrity, sports celebrity, and it should identify which celebrity is that. So this is one of my projects, and this is all the cropping stuff and all. And you can see in the training, this is the main uh, line which is helpful for the looking at the evaluation metrics of a specific project. In that, our perfect fit was 60%, like our model got into 60% accuracy. And then these are all the precision recall and exponent support. Support just means that how many pictures are supported by model, and you can see precision recall F1 and all. As I told you, F1 for F1, the average. If it is closer to 1, it's a really best model. If it is closer to 0, it's a worst model going. So that is good. And then let's say, okay, we have come to the conclusion of this evaluation matrix. Let's say uh, you knew all the types of models till now. Let's say for this type of model, you have SVM, which is a type of model. I think you haven't learned this tool. You will be learning it tomorrow, I guess, in months or whatever. And random forest, you have learned this, and logistic also you have learned it. So out of these three models I knew, I think these three models fit for my model. And I just want to check which model can perfectly apt for this sort of project. And I have seen that SVM gives me 63% accuracy, and random forest gave me 60%, and logistic regression gave me 69%. So out of these three, the majority was 69%, right? So then I'll be using the logistic regression for my model training because that gave me the much accurate value. And this is calculated based on the best estimator. But if you calculate based on the best score, SVM gave me 77%, random forest gave me 60, and logistic regression gave me 81%. Here as well, logistic regression was much higher. So, in considering both the values, I'll be taking logistic regression for my model training. So, this way, you need to look at which model can best suit my supporting project. This way, you need to choose. And I think we are done for today. Any doubts till now? Okay, then I'll just wrap up the session for now. Thank you. If you have any doubt, just feel free to ask me, or just you can post the question in the classroom as well. Any one of our batch can reply for that. Okay, thank you guys.